let's look at a concrete example of big O notation. So consider the functions f of n equal to n squared plus 2n plus 1 and g of n equal to n squared. And our claim is that this f of n here is going to be big O of n squared. And so what do we have to do to prove this? So to prove this, we need to find constants. So we need to find constants c larger than 0 and n0 larger than 0 such that if n is larger than n0 or larger or equal, whenever n is larger or equal than n0, this implies in n squared plus 2n plus 1 is smaller or equal than c times n squared. One convenient choice here, so here we can just take c equal to 4 and n0 equal to 1, and then indeed if we look at it, we're going to have, so then n squared plus 2n plus 1, this will be less or equal, so here this 1 here is smaller than n squared for n larger than 1, so this means that this is going to be n squared plus 2n squared. So think of it as this. So for n larger than n0 equal to 1, we have the following. N squared is going to be equal to n squared, 2n is going to be smaller or equal than 2n squared, and 1 is going to be smaller or equal than n squared, and so this is going to be equal to 4 times n squared, which is exactly our c. So that means f of n smaller or equal than 4 times g of n. And so this proves that indeed n squared plus 2n plus 1 is big O of n squared. Let's do a drawing to help visualize what's happening here. So the idea is that in this case here, let's say this is our parabola f of n equal to n squared plus 2n plus 1, and what's happening here is this is going to be our parabola. Oh, let me improve the drawing here. It's going to be our parabola g of n equal to n to 4n squared. So this is not actually, so this would be actually the constant times g of n equal to 4n squared. And so the idea is that even though f of n might be larger than, let's say, this constant for in the beginning, there is going to exist a point here. So there's going to be this point here, and this point is exactly n0. And the property is that for n larger than n0, so let's make this clear. So this is the n-axis. So for any n larger than n0, this constant here times g of n, in this case 4n squared, is going to be larger than our function. And that's what we mean when we were saying that what we're saying is that g of n, c times g of n, is eventually larger than f of n. That means there exists a moment after which it's larger than that, right? Okay, so this is how you can show something like this. And now let's see some of the rules, some useful rules that can help us work with big O notation. So if we have functions f, h, g, and k from the natural numbers to the reals, and and we have everything for sufficiently large n. So let's say that you're taking everything for, because remember that this is all about eventually, so for large enough n. So if f is big O of g and h is big O of k, then you can show that f plus h is going to be equal to big O of g plus k, and that this is just going to be equal to big O of the maximum of these two functions. Now, and we're going to see examples, but for now let's just talk about the rules. So if f is big O of g and h is big O of k, then if you multiply them, you get big O of the multiplication. If you multiply by a constant, so if you have f is big O of g and a positive constant, then if you multiply, it doesn't change anything. So it's still big O of g. And this pops up sometimes also when you're analyzing algorithms. Sometimes your algorithms are of the form n to the power of some constant and n to the power of some other constant. Then if you have n to the a plus n to the b, for example, then this is going to be big O of the maximum of these two. And so maybe the easiest thing is just to see some examples. So let's say we want to compute these big O's here. So here we can use the sum rule essentially. So this is just going to be big O of the sum. And so this is going to be big O of n squared, big O of n, and a constant. And remember that we then just take the maximum of them. So this will just be big O of n squared. For the bottom one, this is going to be contributing n cubed, but this term here contributes n cubed log n, and so this will be larger. And so here it's just going to be big O of n cubed log n. So we use the sum and also the product rule for this. The bottom one, you can open it up, and but even looking at it, you could ask yourself, what's going to be the dominant term, the largest thing? It'll be just taking the largest from each side, so this n squared with the n here. So this is going to be n cubed, but just by looking at it, but we can open it up first. If you open it up, this will give you 4n cubed plus you're going to get 5n squared plus 12n squared plus 15n, and this will just be big O of the largest one of the n cubed. And same here, you can distribute these two, and the largest is just going to be this term here, n squared log n. And again, the bottom one, we've done a similar one, so this is just big O of n squared. So the main skill here is to identify the dominant growth term and ignore constant factors. And so that is what big O notation is designed to capture.